section 4.5 is a big deal, at least the end of 4.5. The beginning of 4.5, big-ish deal, but not as big of a deal. I'm going to write down the problems again just in case they don't show up so well because whatever glare is going on, if I could actually write them down right. Problem 1 wants me to multiply the square root of 2x by the square root of 8x. When we're dealing with radicals, if the indices are the same, you can multiply the radicals directly by just multiplying the radicands together. So in my problem, when I multiply two cube roots, I'm going to get another cube root. Let me just show you on my calculator what I mean about multiplying with radicals. I'll just make a generic multiplication of radicals. Like if I do the square root of 3 times the square root of 5, because they're both square roots, when I multiply, I just multiply the radicands. The square root of 3 times the square root of 5 is just the square root of 15. If the indices were different, if I was multiplying a cube root by a square root, I'd need to get fraction exponents, make the fractions have common denominators. They could really only be multiplied in very specific times. We won't do that in our class. We will only multiply square roots by square roots, cube roots by cube roots, and so forth. And if you multiply cube roots, you get another cube root. So in my problem number 2, where I'm multiplying cube roots, all I'm going to do is multiply the radicands. That's going to involve multiplying the numbers and adding the exponents on the letters. So the numbers under my radicals are 5 and 25. When I multiply those, I get 125. I could do that in my head, but you can use a calculator if you can't. And for the letters, I'm going to add their exponents. Once I get the problem multiplied, I'm going to reduce separately the number from the letter. Cube root of 125, I don't need my calculator for. I have that memorized at 5. And for the letter, I'm going to divide its exponent of 3 by the index of 3. And for 2, my answer is just going to be 5x. Let me switch out this pen, just in case number 3 isn't readable. Number 3 is multiplying two cube roots. It's the cube root of a b to the 5th times, without the times symbol, but it's implied here, the cube root of a to the 8th b. That's number 3, which would be your problem. My number 4 is multiplying two 4th roots, the 4th root of xy cubed, and I put the times sign here, although it's not necessary, it would be implied, times the 4th root of x cubed y to the 9th. When I multiply two 4th roots, I get another 4th root. I can't multiply a 4th root times the cube root. The indices have to be the same. And when I do the multiplying, I'm just going to add the exponents on the letters here. I don't have any coefficients to worry about. But for my letters, the first x has an implied exponent of 1, the second x has a shown exponent of 3, and the y's have the exponents of 3 and 9. When I do the multiplying here, I'm going to get the 4th root of x to the 4th, y to the 12th, and now I'm going to get rid of the radical symbol by dividing. I'm going to do x to the 4 divided by 4, y to the 12 divided by 4, and my answer to this is just going to be x y cubed. Problem 5, if it's not readable, is the square root of 2x times the square root of 2x. That would be your homework problem. Problem 6, the square root of 6x cubed times the square root of 150x to the 5th. I'm going to multiply 6 times 150 on my calculator because that's more than I can handle right now. So the multiplying part, I multiply the coefficients of 6 and 150 and get 900. And I'm going to add the exponents on the x's and get x to the 8th. And then I'm going to separately find the square root of 900 and find the square root of x to the 8th. Square root of 900 I think is 30, but I'll break out my calculator so I don't mess up. So part of my answer is going to be 30. And for a square root, the index is implied 2. I'm going to do the square root of x to the 8th just by dividing the 8 by 2, and I'll get x to the 4th. So my answer for number 6 is just going to be 30x to the 4th. 7 is the square root of 2 times the square root of 18x to the 4th. When you're doing problem 7, you're just going to multiply the 2 and the 18. My problem 8, just again in case it's not readable, is the square root of 3x times the square root of 12x cubed. This first x has an exponent of 1. I'm going to do the multiplying part. I'm going to multiply the 3 times 12, and 3 times 12 is 36. I'm going to add the exponents of 1 and 3 and get a 4. And then I'm separately going to do the square root of 36 and the square root of x to the 4th. I don't need to write the index for the square root of 36 because I don't need it. But for the letter, maybe I'll throw the index of 2 that's implied and divide the exponent divided by the index. And my answer for number 8 should be 6x squared. So hopefully you can do all the odds, 1, 3, 5, and 7. That's the first of 3 kinds of problems in section 4.5. The second kind of problem is just to use the division property of radicals. The division property of radicals basically says if the index is the same, you just divide regularly and leave the index. So I'm going to divide and then simplify. And going for a darker marker. I feel like this is showing up as well as I want. Not sure that this is going to be any better. Problem 9 is the square root of 12x cubed divided by the square root of 3x. I'm going to do my problem 10. If the indices are the same, then I'm allowed to divide by just dividing the radicands. If the indices are different, like if I had a square root and a cube root, I couldn't simplify without making fraction exponents. So for this problem, what I'm going to do in problem 10 is just reduce the fraction 54y to the 7th over 2y. And whatever that reduces to, I'm going to temporarily leave it under the cube root. I'm going to do the division first, and then I'm going to simplify the radical. Under my radical sign, I have 54 divided by 2, which is 27. So part of the simplifying, the number part's going to be 27. And for the letters, I'm going to subtract the exponents. The exponent in the numerator is a written 7. In the denominator, it's an assumed 1. I'm going to subtract and leave the letter where the bigger exponent is, so the y is going to wind up in the numerator. And now I'm going to do the cube root of 27, which I could do in my head, and the cube root of y to the 6, which I also could do in my head. The cube root of 27 is 3. Could do it on my calculator if I didn't know it. And for the y, I'm just going to divide the 6 by 3 and get 2. So my answer for number 10 is just going to be 3y squared. The problem 11 is the cube root of 24x divided by the cube root of 3x to the 4th. This should feel quite a bit like problem 12. And my problem 12 is the 4th root of 32x over the 4th root of 2x to the 9th. So really, I'm going to divide the radicands and make them all under a single 4th root. So I'll do the 4th root of 32x over 2x to the 9th. I'm going to reduce the fraction 32 over 2. That reduces the 16 in the numerator because the bigger number is in the numerator. And for the letters, I subtract the exponents. The letter in the numerator has an exponent of 1 and the denominator has an exponent of 9. I'm going to do big exponent 9 minus small exponent 1 and leave the x in the denominator because the bigger exponent is there. To finish it up, I'm going to do the 4th root of 16. And whatever that reduces to is going to belong in the numerator. And for the letter in the denominator, or the variable in the denominator, I'm just going to divide the 8 by 4, and the exponent of the x is going to be 2. 13, the square root of 8x to the 5th over the square root of 2x should be similar to 14, which is the cube root of 16x to the 5th over the cube root of 2x squared. So when I reduce a division problem when they're both the same index, I'm just going to reduce the fraction. Here, the 16 divided by 2 is going to be 8. And for the x's, I'm going to subtract the exponents. The x is going to wind up in the numerator because the bigger exponent's in the numerator, and I'm going to get an x cubed. No fraction will be left here because the 8 winds up in the numerator and the x winds up in the numerator. And then I'm going to do the cube root of 8, which I have memorized, and the cube root of x cubed, which I do by dividing the exponent. The cube root of 8 is 2, and for the x, I'm technically dividing this exponent by the index, and that's going to give me an exponent of 1. So my answer for 14 is just going to be 2x. 15 wants me to divide the square root of 4x to the 5th divided by the square root of 4x to the 9th. Let me do 15 instead of 16 just to do one of your homework problems. So this is going to be the square root of 4x to the 5th over 4x to the 9th. The 4's are going to cancel, and the x's have to wind up in the denominator because when I'm dividing and there's positive exponents and the bases are the same, I subtract the big exponent minus the small exponent. I leave the variable or the letter where the bigger exponent is. So the x is going to wind up in the denominator. I can't write a fraction without a numerator. In the numerator, it's just going to be the 4 divided by 4, which is 1. And now I'm separately going to do the square root of 1 and the square root of x to the 4th. Square root of 1 is just 1. And in my numerator, I'm just going to write a 1. And in the denominator, I divide the exponent by the index. I wrote the 2 in here because I knew I was going to need it. My answer for problem 15 is going to be 1 over x squared. So you should be able to do all the odds between 1 and 15. Those are important, but not near as important as the rest of the problems in this section. The rest of the problems in this section involve reducing radicals. And my calculator is beautiful. It knows how to reduce radicals just fine. Problem 17 wants me to reduce the radical, the square root of 50. And to reduce the square root of 50, if I didn't naturally know how to do it, I could just type it in on this calculator. And my calculator tells me that the square root of 50 reduces to 5 times the square root of 2. To reduce a square root by hand, or a square root is reducible if there's a perfect square that divides evenly into the radicand. So there's 2 ways to reduce by hand. At least just with numbers, and I'll get to letters or variables later. So there's 2 ways to reduce number radicals. There's just a number under that radical. By hand. One is to rewrite the problem, the expression, as the multiplication of 2 radicals. And very specifically chosen radicals, and it requires being a little bit clever. So if I wanted to reduce the square root of 50, one way to do it is to rewrite it as a multiplication of 2 radicals. The first radical, its radicand, is going to be the largest perfect square that divides evenly into the radicand. In this case, the largest perfect square that divides evenly into 50. If I look at my perfect squares, 1 squared is 1, 2 squared is 4. These are my perfect squares. And I'm looking for the largest perfect square that if you divide it, 50 divided by it, that you get a integer. 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. If I could scan this list and find a number that goes evenly into 50, I can put that number in my first radical. And in this list, 25 is the only number other than 1 that goes evenly into 50. It's the biggest perfect square. These are all the perfect squares less than 50, and I need to find the perfect square that's less than 50 that divides evenly into 50. And 25 would be that number because 25 divides evenly into 50. In the second radical, I'm just going to take the 50 that I started with and divide by the number I put in the first radical, whatever that happens to be. So my second radical, I'm going to do 50 divided by 25, which is 2. This is a true statement here. The square root of 50 equals the square root of 25 times the square root of 2, because if I was reducing this side, I would multiply the 25 and the 2. 25 is a perfect square root. I know that the square root of 25 is 5. And so when my calculator wrote 5 square root of 2, this is probably what it was programmed to do. It was programmed to find the biggest perfect square that divides evenly into the radicand, split the radical into a product of 2 radicals. The first radical reduces. The second radical isn't reducible. For a radical to be reducible, there has to be a number that divides evenly into the radicand that's a perfect square. That's the clever way to reduce and not the way that I generally teach reducing. The second way to reduce is the prime factor tree method. So I'm going to make a prime factor tree for 50. 50 is not a prime number, and to do a prime factor tree, I usually take the number I'm doing a prime factor tree for and write like a V under it, and on either side of that V are any 2 numbers that multiply out to be 50. The ones I can think of are 5 and 10. 5 is a prime number, I'm going to circle it. 10 is not prime, I'm going to make a branch. Beneath the 10, I'm going to do the same thing. I'm going to put my 2 numbers that multiply out to be 10. The only 2 that I can think of are 5 times 2. 5 is prime and 2 is prime. So the prime factoring for 50 is 2 times 5 times 5. This is enough for me to reduce the radical. When I'm reducing square roots, single numbers, stay under the radical. So when I looked at my answer, this 2, that's a single factor, goes under my radical. And for each pair, you get 1 out front. And so I have a pair of 5s. 1 of those goes out front. This is actually the way that turns out to be easier if you own this lovely calculator, because this calculator does prime factor trees. Let me move on to problem 18, and then I'll probably have to pause the video. 18 wants me to reduce the square root of 24. there's two methods. The write as the product of two square roots. That's probably how I do the problem, but not how I teach it. So what I have to do is I have to find the largest perfect square that divides evenly into 24. I'm not going to worry about 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. I look at the lists of perfect squares that are less than 24, and I ask myself, is 24 divided by 16 an integer? If it is, I'd put 16 in that radical, but it's not. Is 24 divided by 9 an integer? No, but 24 divided by 4 is an integer. I'm going to break this up into 24 equal to 4 times 6, because 24 divided by 4 is 6. Then I'm going to do the square root of 4, which is 2. This is going to give me 2 square root of 6. The video is going to hiccup here in a second. On my calculator, if I do the square root of 24, I get 2 rad 6. I'm going to put the rest of this in a part 2 because my video is going to hiccup.